Welcome back to the deep dive. You know, every time I get into a new car these days, I feel like I'm kind of stepping into a deception.
A deception. That is a pretty strong opening.
It is, but hear me out on this. You sit down and you see the massive touchscreens, the ambient lighting, the heads-up display projecting all these arrows onto the road. It feels futuristic. It feels like science fiction. But if you were to peel back the leather and the plastic and actually look at the skeleton of the machine, well, in most cars, you'd find architecture from the 1990s.
You're really not wrong. We dress them up like spaceships, but underneath, most of them are still operating on what we call a distributed architecture, which is a polite way of saying organized chaos.
Exactly. And that is what we're tearing apart today. We have a massive stack of research here for you. We're talking deep tech strategy papers from Murata, NXP, Renesas Onsemi, and they are all pointing to the exact same conclusion, which is that the automotive industry has hit a wall. And not a metaphorical wall, but a literal physical limit.
Right, we call it the physical wall.
The physical wall. And the blueprint we are looking at today, the 2026 blueprint, is how engineers are actively trying to break through that wall. We aren't just talking about putting in a faster processor or, better camera. We are decoding a total anatomical reinvention of the automobile.
We really are. We're moving from a car that just happens to have computers in it to a mobile data center that happens to have wheels.
Yeah, and that distinction matters immensely for you as the listener, because up until now, the approach has been purely additive. You want heated seats, add a heated seat computer and a wire. You want lane keep assist.
Add a camera, a computer, and another wire.
The add-on method.
Precisely. But the result of that is that a modern luxury SUV might have 150 different computers. We call them electronic control units or ECUs, and they are scattered all over the frame. And connecting them is this massive wiring harness that weighs nearly 150 pounds and stretches for literally miles if you laid it all out.
That is the physical wall right there. You literally cannot fit any more wires into the chassis.
You can't fit them, you can't cool them, and honestly, you can't afford the weight. In the EV era, weight is the absolute enemy of range. So if you want a car that is truly software-defined, meaning it updates like your phone and gets smarter over time, you cannot build it on this old, heavy, fragmented foundation. You need a clean sheet of paper.
So today we are looking at that clean sheet. And based on these strategy reports, we've organized this deep dive into 4 distinct pillars. First is the topology, which is the actual physical layout of the car. Second is the brains, so the silicon and the sensors. Third is the muscle, looking at high voltage power integration. And fourth is the nervous system, the communication network.
And we really have to start with the topology, because if you get the layout wrong, then nothing else matters.
Let's get right into it then. Segment 1 is the zonal revolution.
To understand zonal, you first have to understand how incredibly inefficient the current domain system is. Right now, cars are organized by function, so you have a body domain controller usually somewhere tucked in the dashboard, and it controls the windows, the locks, the lights. But the windows and the locks are obviously at the 4 corners of the car, so you have to run individual copper wires from that central dashboard controller all the way out to
the rear left door, the rear right door, the trunk, the hood.
Exactly. It's a star pattern, but it's a very messy one.
So if I roll down my rear left window, the signal goes from the switch in the door all the way to the dash, and then the physical power is sent all the way back to the motor in the door.
It is incredibly wasteful. Zonal architecture completely flips this paradigm. It ignores function entirely and focuses strictly on physical location.
So geography over function.
Right. We divide the car into physical zones: front left, front right, rear left, rear right. And in each of those zones, we place a zonal control unit, a ZCU.
The ZCU. So this is like the new middle manager of the car.
Think of it as a local hub or an aggregator. The rear left DCU handles absolutely everything in that corner. It doesn't matter if it's a taillight, a window motor, a tire pressure sensor, or an audio speaker. If it is physically in that corner, the ZCU controls it.
So the central computer just sends one single command, something like open rear left window. It sends that data via one high-speed cable to the rear left CCU, and then the ZCU hand the actual power distribution to the motor right there.
Correct. And the commercial implication for manufacturing is massive. You get rid of that giant octopus wiring harness. Instead, robots can build the car in modular chunks. You build the rear left corner, you install the ZCU, and you just plug it into the main backbone.
And what about the copper savings?
The reports suggest a 40 to 60% reduction in wiring harness weight and length. That is huge. That is copper you don't have to mine, it saves money, and it's dead weight the battery doesn't have to carry around.
But there is always a catch in engineering. And this introduces a new nightmare that the Murata report calls the density challenge.
Oh, yes. This is where the physics gets really mean.
I was looking at this section, and in the old system, the computers were mostly in the dashboard or the trunk. They were relatively safe, dry, climate-controlled.
Generally, yes.
But if we are moving these ZCUs out to the physical zones, that means they're going into the wheel arches. They're going under the hoods next to radiators. They're going inside the bumpers.
They're going into the absolute harshest environments possible. We are talking about severe vibration, moisture, and most critically, heat. The industry standard for these locations is automotive grade 0, and that means the component has to survive and operate at 150 degrees Celsius.
150 Celsius, that is over 300 degrees Fahrenheit. That is literal baking temperature.
It really is. If you put your laptop in an oven at 300 degrees Fahrenheit, it wouldn't just turn off. The solder joints would melt. The plastic would warp, the capacitors would leak. But these ZCUs have to operate safety-critical systems like brakes and steering in that heat for 15 years.
And it's not just the ambient heat from the road or the engine, right? These ZCUs are actively distributing power. They act as the local fuse box. So they are generating their own intense heat internally.
Exactly. You are running high current through a tiny sealed box in a blistering hot environment. This forces a complete change in the material science of the underlying components. You simply cannot use standard electronics.
The Murata report specifically highlights a shift to metal alloy inductors, the DFE series. Now, I know generally what an inductor does. It stores energy in a magnetic field to smooth out power. But why does the physical material matter so much here? Why can't we just use the normal stuff?
So traditional inductors use a ferrite core, basically a ceramic material containing iron oxide, and they are great for general electronics. But ferrite has a severe weakness, which is saturation.
Saturation. Break that concept down for us.
Think of an inductor like a sponge that soaks up water, and the water is the magnetic field. A ferrite sponge is relatively small. If you hit it with a massive spike of current, say a window motor jamming and drawing huge power, the sponge gets full instantly. It saturates.
And when it's full,
It stops acting like a sponge entirely. The water just spills everywhere. In electrical terms, the inductance drops to 0 and the component just becomes a bare wire. You lose all your power filtering. The voltage ripples violently and that electrical noise instantly crashes the computer.
which, if that ZCU is currently controlling your anti-lock brakes, is an absolute catastrophe.
Exactly. You cannot have the central brain crash just because a window motor got stuck. So the shift is to metal alloy inductors. These use a metallic magnetic powder that is molded directly around the copper coil.
And how does that change our sponge analogy?
It turns it into a sponge with infinitely more pores. It has a significantly higher saturation current. You can hammer it with massive high current spikes, even at 150 degrees Celsius, and it will not saturate. It maintains its inductance. It keeps the power delivery perfectly smooth.
So the reliability of this entire futuristic zonal architecture actually hangs on the chemistry of this little gray square on the circuit board.
It really does. If you use standard ferrite in a ZCU, it will fail. It is that simple.
The other component that caught my eye in the density challenge section was the capacitors. They're shrinking them down to 0.2 or 0.1 sizes.
Right. 020 refers to the physical dimensions. It's 0.6 millimeters by 0.3 millimeters. It is effectively the size of a speck of dust.
Why on earth do they need to be that small?
Real estate. The ZCU has to do so much work. Power distribution, data aggregation, sensor processing. The circuit board is incredibly crowded. You need thousands of capacitors to stabilize all that power. If you use standard sizes, the board becomes the size of a pizza box, but you need it to be the size of a paperback book to fit in the wheel arch.
But doesn't shrinking them down make them incredibly fragile? Cars vibrate constantly.
That is the big trade-off. Ceramics are brittle by nature. If the circuit board flexes because the car hit a pothole, a standard ceramic capacitor might crack. And if it cracks, it can cause a short circuit. So manufacturers like Murata have to engineer these microscopic conductive resin layers inside the capacitor to act as physical shock absorbers.
Microscopic shock absorbers built into the capacitors.
It is the only way to make something that tiny roadworthy.
Before we leave the zone, I have to ask about the digital fuse box concept. This feels like a quality of life upgrade that is just decades overdue. We have all had a fuse blow in an older car. You have to find the box under the dash, pull out the little plastic thing with tweezers, hold it up to the light to see if the wire is broken.
It is archaic. A melting wire is quite literally 19th century technology. In the zonal architecture, we are finally moving to E-fuses, or what they call smart power stages.
So these are solid-state silicon switches.
Yes. They are high-side switches that constantly monitor the current flowing through them. If they see a dangerous spike like a short circuit, they just turn off. They don't melt. They simply open the circuit electronically.
And because they are silicon, they are connected to the vehicle software.
That is the game changer. A physical melting fuse tells you nothing. It just dies. An E-fuse tells the ZCU, hey, I saw a 15-amp spike on the rear wiper motor at exactly 2 p.m.
Precision diagnostic data.
Huge amounts of diagnostic data. And it allows for self-healing. Let's say the spike was just a total fluke, a weird transient voltage event. The software can decide to wait 100 milliseconds and then try to safely reset the fuse.
Just automatically.
Automatically via over-the-air parameters. You might never even know it happened. Or if it is a real persistent fault, the car can send a clear notification to your dashboard screen saying, check rear wiper for obstruction, instead of the wiper just stopping dead in a rainstorm. It turns a hardware failure into a gracefully managed software event.
That right there is a definition of a software-defined vehicle.
Yeah.
Okay, so we have the zones handling the limbs and the local power. They need a boss. They need a brain to process all this data. Let's move to segment 2, CPU and sensors.
The high-performance compute, or HPC.
The strategy here from reports is massive centralization. Instead of having medium-power computers everywhere, we are putting massive server-grade silicon right in the middle of the car.
We are talking about 5-nanometer and 7-nanometer system-on-chips, or SOCAS. These are literally the exact same class of chips you would find in a PlayStation 5 or a high-end AI server farm.
But bringing that kind of bleeding-edge silicon into a car introduces what the NXP and Renesas reports call the power paradox.
Right. And this is something people often misunderstand about electronics. They think, oh, chips are getting smaller and more efficient, so power must be getting easier to manage. It is actually the exact opposite.
Explain that for us.
As you shrink the transistors on a chip to make them faster and pack more in, you have to lower the operating voltage. These modern 5-nanometer chips run at incredibly low voltages, often less than 0.9 volts.
Less than a single volt.
Less than a volt. But to do the actual work, to run the massive neural networks for autonomous driving or large language models in the cabin, they need massive total power. And power equals voltage times current. So if your voltage goes down, your current must go massively up to compensate. So these tiny chips are drawing hundreds of amperes of current.
Hundreds of amps. A typical house circuit for a room is like 15 or 20 amps.
Exactly. You are pushing house-level current through a tiny piece of silicon at less than 1 volt. The paradox is the stability required. The report mentions a voltage tolerance of plus or minus 30 millivolts.
Right, 0.0 to 3 volts.
That is your entire margin of error. If the voltage drops by more than 0.03 volts, the processor effectively gets confused. It might flip a bit in memory. A 0 accidentally becomes a 1.
A calculation error.
And if that calculation is determining, is that a pedestrian or is that just a shadow, you cannot afford a single error. So you have this incredibly fragile power requirement. And the real problem is the computational load is highly dynamic. 1 millisecond, the AI is idle, and the next millisecond, it is suddenly processing 4K video from 8 different cameras. The current demand spikes instantly.
It's like turning on a massive fire hose inside a tiny garden hose. The pressure or the voltage is just going to drop immediately.
That is a perfect analogy. That drop is called voltage droop. And if it droops more than 30 millivolts, the entire central brain of the car crashes.
So how do you prevent that droop? The main battery is way far away in the floor pan.
You need a distributed power architecture. You can't just have one big power supply. You have a main system PMIC or a power management IC that takes the 12 volts from the car and steps it down. But then right next to the processor, literally millimeters away, you have sub-PMICs.
Like local voltage regulators.
Yes, but even those active regulators aren't fast enough for the nanosecond spikes of a modern AI chip. That is where the capacitors come back into the story. The report highlights low ESL capacitors, specifically these LW reverse types.
ESL stands for equivalent series inductance.
Right. Think of the capacitor as a small water tank placed right next to your fire hose. When the hose opens up, the tank dumps its water instantly to keep the pressure up, while the main supply from the PMIC catches up.
Okay, I follow that.
ESL, or inductance, is essentially the width of the pipe coming out of that water tank. A standard capacitor has a narrow pipe. It simply can't dump the electrical energy fast enough. An LW reverse capacitor is physically designed with a massive wide pipe. It has ultra-low inductance.
So it can dump its entire charge instantly.
Instantly. It fills that 30 millivolt hole before the processor even realizes there was a demand spike. Without these specific low ESL 3-terminal capacitors, those 5-nanometer AI chips simply would not function in a car. They would crash every single time they tried to think hard.
It is genuinely amazing how the absolute cutting edge of artificial intelligence depends entirely on the physics of a passive component.
Power integrity is absolutely the unsung hero of the AI revolution in automotive.
Let's shift to the inputs for that brain. The eyes, the sensor fusion.
This is where we see the megapixel race finally stabilizing.
Right.
For a while in the industry, it was just more is always better. But the major players are converging on 8.3 megapixels for the primary front-facing cameras.
That seems very specific. Why exactly 8.3?
It comes down to the math of autonomy. To drive safely at highway speeds, say 120 kilometers per hour, the car needs to be able to identify a very small object like a tire tread or a brick on the road from about 200 to 400 meters away.
So quarter of a mile out.
Right. To physically resolve an object that small at that extreme distance, you need a specific pixel density on the sensor. 8.3 megapixels is the minimum resolution that guarantees that detail at that range.
But why stop there? Why not go to 20 megapixels or 50 like our smartphones?
Data overload. Every single pixel you add is data that the central HPC has to process in real time. If you go to 20 megapixels, you might be able to see further, but you completely drown the computer in data, which increases the latency of the decision. 8.3 megapixels is the Goldilocks zone. It is enough detail for L3 safety, but it remains manageable for the silicon bandwidth.
I really want to touch on the Hyperlux technology mentioned in the Onsemi report. They talk heavily about 150 dB HDR. Now, I know high dynamic range from buying a TV, but why is 150 dB such a critical number for vehicle safety?
This solves what we call the tunnel problem.
The tunnel problem.
Imagine you are driving into a dark tunnel on a very bright, sunny day. To your eyes, the entrance looks almost like a black hole.
My eyes usually take a second or two to adjust.
Or, conversely, you are inside the dark tunnel driving out. The exit looks like a blinding white square. A standard camera sensor has a very limited dynamic range. It can expose for the dark tunnel, which blows out the exit to pure white, or it can expose for the bright exit, which crushes the tunnel into pure black. It physically can't do both at once.
Which means for a split second, the car is essentially blind.
And a blind autonomous car at highway speeds is a lethal car. 150 dB is a massive dynamic range capability. It allows the sensor to capture the subtle texture of the asphalt inside the dark tunnel and the crisp details of the clouds outside the tunnel in the exact same frame at the exact same time.
So it doesn't have to choose between light and dark.
It sees absolutely everything.
Yeah.
And Hyperlux uses a technique called superexposure to do this instantly without the motion blur or ghosting artifacts you used to get with older HDR methods that combined multiple frames.
There is another acronym in the sensor section, LFM, LED flicker mitigation. This one I have actually seen in action. If you film a modern car's taillight with your smartphone camera, it often looks like it is strobing or flashing.
Yes, it does. That is because LEDs don't actually dim by lowering the voltage. They dim by turning completely on and completely off really, really fast. It is called pulse width modulation, or PWM.
Our human eyes just average it out so it looks like a solid, dim red light.
But a high-speed camera has a very fast shutter speed. It might snap a picture exactly when the LED happens to be in its off cycle.
So the camera sees a completely dark taillight.
Or a dark traffic light. Or an unlit digital speed limit sign. If the AI catches a sequence of off frames, it might conclude that the car ahead has its brake lights off, or that the traffic light is broken.
That sounds incredibly dangerous for a self-driving system.
It is unacceptable. LFM is a specialized sensor technology that ensures the exposure window captures the light pulse no matter when it happens in the PWM cycle. It mathematically reconstructs a solid continuous light source for the AI. It totally prevents the car from hallucinating that a red light has turned off.
One last sensor technology before we move on. What happens when the external sensors fail completely? Say you are driving into a deep concrete parking garage, 5 floors underground. No GNSS, no cellular, no optical landmarks.
This is the fascinating realm of dead reckoning.
It sounds like the title of a pirate movie.
It actually comes from ancient sailing. If a navigator can't see the stars, they calculate exactly where they are based solely on how fast they were going and which way they turned from their last known position.
How does a car do that underground?
With a 6 degrees of freedom inertial measurement unit, an IMU, Murata's SCH-16T is the industry benchmark highlighted here. It is a tiny silicon chip packed with microscopic gyroscopes and accelerometers.
So it acts as the inner ear of the car.
Precisely. It senses balance and movement. But the precision required is insane. If the gyroscope drifts even a fraction of a degree, over a mile of driving without GPS, the car will mathematically think it is in the oncoming lane. The SCH-16T is so precise that if you enter a 5-mile tunnel, it can track every single lane change, every slight curve, and every acceleration pedal press, and tell you exactly where you are within centimeters when you finally exit.
Without seeing a single satellite the entire time.
Purely based on measuring the physics of motion. It provides the absolute redundancy that allows us to trust the machine when the sky is completely blocked.
So we have built the zonal body and we have built the silicon brain. Now we need the muscle to move it. Segment 3 is X-in-1 integration.
This is the true powertrain revolution for EVs.
We have all heard of 3-in-1 axles, right? The
Yeah.
motor, the inverter, and the gearbox bolted together. But the report talks about X-in-1, things like 8-in-1 or even 12-in-1 systems. We are smashing literally everything into a single physical box.
We are. The onboard charger, or OBC, the DC-DC converter, the battery management system, the vehicle control unit. Engineers are successfully putting it all into one shared housing.
I totally get the commercial benefits of that. Better packaging, lower weight, reduced bill of materials. But the NXP report raises a massive red flag here. They call it the mixed criticality nightmare.
This is arguably the biggest software engineering headache in the EV space right now.
Explain mixed criticality for us.
In the automotive world, safety is graded by ASIL, Automotive Safety Integrity Level. ASIL D is the absolute highest rating. That is your brakes, your steering, your traction inverter that spins the wheels. If these systems fail, people die.
Very serious stuff.
Then on the other end, you have QM, which stands for Quality Managed. This is stuff like your air conditioning compressor or your cabin radio. If it fails, it is super annoying, but nobody gets hurt.
Okay, makes sense.
In a deep X-in-1 integrated system, you are putting the inverter, which is ASIL D, and the thermal management for the AC, which is QM, on the exact same silicon chip to save money and space.
Wait, hold on. You are putting the code that physically stops the car on the same processor as the code that cools the cabin.
Yes. And here is the core problem. QM software is usually much less rigorously tested. It might have bugs, it might suffer a memory leak and crash.
If the AC software crashes, does it take down the inverter code with it?
In a standard computer architecture, yes, absolutely. A memory leak in the AC app could just overwrite the memory block currently being used by the braking algorithms.
But that sounds like a massive lawsuit waiting to happen. My AC broke, so my brakes failed.
It would be disastrous. That is exactly why you need hardware isolation. You simply cannot trust the software layers to play nice with each other. You need a hardware cop enforcing the rules.
The report specifically mentions the NXP S32 platform and something called XRDC.
XRDC stands for Extended Resource Domain Controller. Think of it as a series of impenetrable steel walls physically built inside the chip. The XRDC physically prevents the low-safety QM cores from ever accessing the memory addresses or the hardware peripherals assigned to the ASIL D cores.
So it's a literal hardware firewall.
Exactly. Even if the AC software goes completely rogue and aggressively tries to write garbage data to the inverter's memory address, the XRDC intercepts that request at the silicon layer and completely blocks it. It returns an access denied error. The AC might crash hard, but the inverter keeps spinning the wheels perfectly.
And this is what the industry calls freedom from interference.
FFI. It is the absolute gold standard for ISO 26262 safety compliance. It allows us to harvest the incredible cost and weight benefits of integration using one chip to run everything without ever compromising the safety of the critical driving systems.
There's another physical aspect of X-in-1 that fascinated me in these papers: embedded packaging. We aren't just integrating the control chips, we are fully integrating the high-voltage power modules themselves.
Yes. Traditionally, a power module, the heavy thing that actually switches the high voltage for the motor, was a separate, bulky brick screwed onto a metal heatsink. Now we are seeing chip embedding technology. They are placing the bare silicon carbide or gallium nitride power dies directly inside the printed circuit board layers.
Wait inside the actual circuit board.
Buried right in the inner layers. This drastically reduces what we call parasitic inductance.
There's that word again. Inductance.
In this specific case, it is the resistance to changing current caused by the physical length of the wire leads connecting the chip. By burying the bare chip inside the board, the connection distance becomes microscopic. Less inductance means less heat generated and much faster switching speeds. But of course, it creates a new thermal challenge. You are now generating intense heat deep inside the board itself.
So internal cooling becomes even more critical.
It does. But if you can solve the cooling, you get a power system that is literally half the physical size and up to 20% more efficient than the old brick method. Plus, you drastically reduce the electromagnetic interference.
Which brings us perfectly to the fourth and final pillar. We have the zonal body, the multi-domain brain, the integrated muscle. Now we absolutely need the nervous system to connect them. Segment forward is communication.
The great data explosion.
The report mentions that we are rapidly hitting the Shannon limit with traditional copper wire. Now, I have heard of Moore's law for transistors, but what exactly is the Shannon limit in this context?
The Shannon limit is a fundamental theoretical maximum for how much digital data you can possibly push through a given physical channel before the background noise completely overwhelms the signal.
And the channel here is a standard copper wire.
Right. With all these 8-megapixel cameras and radar, we are trying to push 10, 25, maybe even 50 gigabits per second through the car's network. To do that on copper, you have to use incredibly high frequencies. But here is the physics problem. At those extreme frequencies, copper stops acting like a simple pipe and starts acting like a radio antenna.
So it radiates energy out.
It radiates energy out, but much more importantly, it sucks electromagnetic noise in. And an EV is a terrible environment for noise. You have that massive X-in-1 motor switching high voltage thousands of times a second right next to it. It is a literal electromagnetic hurricane under the floor.
So if you try to run a high-speed copper Ethernet cable past the motor, the data just gets corrupted.
Unless you heavily shield it. But shielding means wrapping the wire in thick metallic foil and heavy braided metal. That makes the wire incredibly heavy, very stiff, and super expensive. You end up right back at the physical wall of weight we talked about.
So the solution is to abandon copper entirely for the high-speed backbone lanes.
Enter optical Ethernet, specifically the IE 802.3 SYNCIA's standard. We are switching to plastic optical fiber, or POF.
Why plastic, though? I always thought pure glass was better for fiber optics.
Glass is definitely better for running internet cables under the ocean, but glass shatters. Cars vibrate constantly, they go over speed bumps, they occasionally crash, the chassis flexes. Plastic optical fiber is incredibly rugged. You can bend it, you can vibrate it, and it survives perfectly.
And what about the electromagnetic noise from the motor?
Photons are completely immune to electromagnetism. The traction motor can scream all it wants. The light signal bouncing inside the plastic fiber remains perfectly clean. Absolutely zero metal shielding required.
So it is significantly lighter, vastly faster, and totally immune to noise.
It is the inevitable backbone for the software-defined vehicle. It is the massive interstate highway of the car.
But obviously we can't afford to run fiber optics to every single door handle and window switch. That would be insane overkill.
Correct. So we have a tiered network system, optical for the main central backbone, but out at the edges, connecting to the zones, we have a new hero, which is CAN XL.
The CAN bus. It is like the cockroach of automotive networks. So it's been around since the 1980s, and it just absolutely will not die.
It won't die because it is incredibly cheap and bulletproof. But CAN XL is a massive architectural evolution. It boosts the raw speed up to 10 or 20 megabits per second, which is decent for edge devices. But the true killer feature is IP tunneling.
Explain that mechanism. How do you tunnel internet protocol through a basic CAN network?
Think of CAN XL as a fleet of container trucks. In the old days, classic CAN could only carry tiny little packages, just 8 bytes of data per frame. You physically couldn't fit a standard Ethernet data packet inside it.
Too small of a truck.
Exactly. CAN XL increases the payload space to 2048 bytes. That is plenty big enough to hold an entire standard Ethernet frame. So the software in the central brain can just send a standard TCP IP message, the exact same language the entire internet uses, and the ZCU can just stuff that message inside a CAN XL truck and drive it down a cheap wire to the door handle.
So the massive central computer doesn't need to learn old CAN language. It just speaks pure Ethernet natively, and the local network handles the translation seamlessly.
Exactly. It completely unifies the software stack. A developer can treat a physical window motor exactly like a network device, just like setting up a smart printer on your office network.
And what about the very extreme edge?
Yeah.
The last meter, so to speak.
For that, we're moving to wireless, Automotive Bluetooth Low Energy, or BLE.
Wireless sensors inside a moving car. Isn't that inherently risky? What if the Bluetooth connection drops like my headphones do?
Well, you obviously wouldn't use it for the steering wheel or the brakes, but for the tire pressure monitoring system, or PPMS, it is absolutely perfect. You can't realistically run a physical wire to a spinning wheel anyway. or even more importantly, the battery management system inside the high voltage pack.
Why inside the battery pack?
The battery pack is a dense maze of hundreds of individual cells. Running a complex wiring harness inside there is heavy and quite dangerous. If a physical wire chafes from vibration and touches a high-voltage cell, you have an instant thermal runaway fire. Wireless BMS puts a tiny standalone radio chip directly on each cell module. No wires to chafe or short out, no physical connectors to vibrate loose over time.
And physical connectors are a huge failure point, aren't they?
The absolute #1 hardware failure point in automotive electronics is the mechanical connector. If you delete the connector, you completely delete the failure mode.
There is one final critical concept for the network architecture. TSN. Time-sensitive networking.
The ultimate traffic cop.
Why does a network this fast even need a traffic cop?
Standard Ethernet, exactly like your home internet, operates on a best effort basis. If you send an important email and it arrives half a second late because someone else in the house was streaming a 4K movie, literally nobody cares.
Right, that latency doesn't matter.
In a car moving at 80 miles an hour, if the central brain sends a break now command and it gets stuck in the network buffer behind a giant 4K video stream going to the kids' infotainment screens in the back seat.
Total disaster.
TSN fundamentally changes the rules of Ethernet. It turns it into a fully deterministic network. It allows the engineers to tightly schedule the data traffic at the microsecond level. You can hard code a rule saying every 1 millisecond the network will absolutely clear a dedicated path for safety data.
So it literally freezes the Netflix stream for a microsecond to let the break signal through.
Effectively, yes. It physically guarantees that the critical control signal arrives exactly when it is mathematically supposed to, with virtually zero jitter. It makes a shared network completely predictable, which is a hard legal requirement for safety certification.
So let's pull this all together. We have gone really deep today. We have looked at the zonal body replacing the domain spaghetti with local hubs, using metal alloy inductors and digital e-fuses. We have seen the incredible 5-nanometer brain with its plus or minus 30 millivolt power struggle and its 150 dB HDR vision. We have explored the X-in-1 integrated muscle protected by hardware firewalls, and we have outlined the optical and deterministic nervous system.
It is a massive amount of engineering.
When you look at this entire 2026 blueprint as a holistic system, what is the ultimate big takeaway for the industry?
The core takeaway is that the car is finally becoming a singular cohesive organism. In the past, a car was really just a collection of disparate parts, a patchwork. You bought an engine controller from Tier 1A, a radio from Tier 1B, and you just wired them together and hoped they worked.
Integration was always an afterthought.
Right. But this new architecture is truly holistic. The silicon hardware is designed from the very ground up specifically to support massive software scale. That physical wall we talked about at the very beginning, this architecture is how we smash right through it. By removing the heavy copper, physically integrating the isolated boxes, and switching to light-based and IP-based communication.
And without this complete hardware foundation, all the grand industry hype about software-defined vehicles and full self-driving is quite literally just marketing fluff.
Completely. You physically cannot run 2026 AI software on 1990 distributed hardware. It simply will not fit, and it will not process fast enough.
I think there is a really provocative thought here, too. For a century, the hardest part of building a car was the physical assembly line, getting the stamping machines and the welding robots to align perfectly. But with this blueprint, the true complexity is shifting away from the factory floor.
That is a great point.
The complexity is moving into the silicon design labs. Designing that XRDC firewall or that low ESL capacitor is now just as critical, if not more critical, than tightening a bolt on the assembly line.
The battleground has moved to the microscopic level.
So the next time you are stuck in traffic just staring at the bumper of the car in front of you,
Don't just look at the red taillight. Think about the PWM signal flickering that light hundreds of times a second. Think about the zonal controller sitting right inside that plastic bumper, baking at 150 degrees, holding the voltage perfectly steady with a tiny metal alloy sponge. Think about the optical fiber pulsing with gigabits of data just inches away.
it is a completely hidden world of extreme engineering humming right beneath the surface.
It truly is, and honestly, it is only getting more complex from here.
My brain is certainly saturated at this point, hopefully not dropping my inductance to zero like a ferret core.
Let's hope you have some metal alloy capacity left for next time.
That is all for this deep dive into the 2026 blueprint. Thank you all so much for listening, and keep looking beneath the surface.
Drive safe, everyone.